Hello and welcome to this, the latest of our monthly webinars from the IEA Clean Coal Centre. My name is Colin Henderson. Thank you for joining me and for braving the introductory music. I'll be talking today about power plant CO2 capture heat integration, which is the topic of my latest report for the Centre. The report has recently been made available on our website. If you're watching from one of our member countries or sponsoring organisations, you can download all the newest reports at no charge after a one-off registration. And anyone anywhere can register and download for free our reports that are over 6 months old. So take a look and see what's available. And the slides that I'll use will be available as a PDF on the website later today. If you have any questions and you think I'll be able to answer them, you'll see that you can submit these using the box near the top of your screen. I'll do my best to answer these after the presentation. The nature of this report, reviewing a fairly specialised but important area of work, makes it not ideally suited for conveying in a presentation such as this, but I'll try to provide an indication of what you'll find in a little more detail in the report, with references to the original work. It's about reducing the energy penalty associated with incorporating CO2 capture on coal-fired power plants. This slide shows a basic configuration of post-combustion capture, as it is often called. The key feature is that the CO2 is scrubbed from the flue gases after they emerge from essentially conventional gas cleaning systems, though they may need some enhancement of their SO2 removal, which doesn't concern us here. Although the main coal-fired power unit appears to be unchanged, there are important modifications that have to be made to produce a workable system, and in particular the CO2 capture system requires substantial inputs of energy to operate. Reducing this energy requirement is key to making CO2 capture economically more attractive. And one of the best ways to do it is to reuse some of the waste heats arising in the capture systems. In other words, to increase the energy integration. To discuss energy savings through integration, I need here to give some more description of the solvent scrubbing system itself. This diagram is from evaluations by Hannock and co-workers referenced in the report. A liquid consisting of a solution of a type of amine is contacted at about 40 degrees Celsius with the cooled flue gas from the boiler. This happens in a packed absorption column or absorber where the CO2 reacts with the amine and so is chemically captured. The CO2-rich solvent is then passed to a stripping column or desorber where the retained CO2 is released as a concentrated stream by adding heat to reverse the chemical reaction of capture and regenerate the solvent for reuse. Substantial quantities of steam have to be taken from the main plant to provide heat for the stripper heater or reboiler, because large flow rates of reagents are needed for absorbing the huge quantities of CO2 produced in combustion, which is about 2.5 times the weight of coal burnt typically, plus the fact that the energy regeneration of CO2 is quite high and you've got to heat the solvent up as well. The steam is taken from the crossover pipe, indicated on this slide in green. It connects the intermediate pressure turbine outlet with the low pressure turbine inlet. So it's quite a big pipe. There are alternatives, but an aqueous solution of monoethanolamine, which is otherwise known as MEA, is the solvent most widely regarded as suitable for first generation capture plants because of its high reactivity and it's been extensively characterized. Waste heat is potentially, but not exclusively, available in the areas arrowed in blue here, and later slides look a bit closer at some of these. Energy usage associated with the CO2 capture systems can result in up to 30% loss of electrical efficiency in the absence of integration measures. The steam extraction has the greatest effect in the form of lost output, as much as 50% of the steam that would normally enter the low-pressure turbine cylinders can be needed to give enough energy to heat the CO2-rich solvent, strip the CO2 off and regenerate the solvent. The resultant loss of power output from the turbine typically accounts for about 2/3 of the overall energy penalty of capture. power to drive fans, compressors and pumps in the capture systems further reduces net output. Utilising in the water steam cycle potential sources of heat from the capture systems will reduce the required amount of steam extraction and so also the associated drop in gross power. Different situations, locations and coal types will affect the possibilities available. This table illustrates the challenge of utilisation of the heats. There are large quantities available, but the temperatures are not high. Novel CO2 compression systems might also reduce the cost and efficiency penalty of capture, and I'll give an example of that later. Studies of heat integration of post-combustion capture plants on pulverised coal power units involve complex modelling and calculation procedures. I'll cover them briefly here, only to keep it simple, and simpler for me too. Let's move on. Allowing for losses in the connecting pipework, a minimum steam pressure of 0.31 megapascals is needed at the point of low pressure steam extraction in order that steam is at the necessary conditions at the reboiler for a normal stripper temperature, which is usually about 120 degrees Celsius. To ensure this, and to protect the turbines, particularly at times of variable load, valves would typically be added as shown here. Since the crossover steam is at a higher than saturation temperature and probably at a higher pressure than 0.31 megapascal, energy in the superheated steam should also be exploited. This might be implemented by incorporating, for example, a heat exchanger for low pressure feed water heating and or a let down turbine before you feed it on to the reboiler. After the steam has been used to give the required reboiler heat, mainly by condensation, the hot condensate is returned to the main water steam cycle at the deaerator storage tank, or shortly ahead of it at a feed water heater. CO2 compression before transport to storage is carried out in stages, with cooling between the stages to control the working temperature and to minimise the energy needed. This heat, and that from the stripper overhead condenser, which are both marked on this slide with that circle, have been identified by a number of researchers, including Pfaff and colleagues in Germany. This figure is from them, as suitable locations to extract waste heat at reasonable temperatures. The waste heat of the stripper overhead condenser is suitable for providing some of the heat for the low pressure boiler feed water, instead of using some of the pre-existing LP heaters in a retrofit. And water wash cooling, you see on the left, is necessary to ensure a water balance. This next slide includes these available heats. I'll talk about compression heat separately with a later slide. Preheating the combustion air was also identified by Pfaff as a possibility. In combination with feed water preheating, the gain in efficiency was about a percentage point. The steam air heater was then not needed, giving an increase in power and an efficiency gain of 0.3 percentage points. Means of minimising the efficiency penalty of adding capture to existing coal plants have been examined in Edinburgh by Lucchio and Gibbons. They showed that initial plant efficiency need not have a significant direct effect on the efficiency penalty in percentage points for a retrofit, and the effect of site-specific parameters is likely to be small compared to the influence of the capture system design. However, this would be subject to the steam extraction pressure being the same for the subcritical and supercritical plants. A couple of slides from them. In the configuration for retrofit with two let-down turbines shown in this slide, the intermediate pressure turbine outlet pressure is fixed, and the let-down turbine at the inlet of the LP turbine will be bypassed if capture were temporarily suspended to give a short-term increase in power, for instance, give us a spinning reserve to the grid. In the example in the next slide, another configuration, again for retrofits, at intermediate load and capture levels, the crossover pressure will actually float, and the let-down turbine will be throttled to vary the steam flow to low-pressure turbine. raising the temperature of recovered heat by employing heat pumps has been assessed by Duan and co-workers in China. The cycle included using heat extraction from the gases leaving the CO2 stripper to supply heat to the evaporator of an absorption heat pump, which is at the bottom right of this diagram. This heat pump, driven by steam extracted from the turbine, converts part of the lower grade heat from the stripper gases to higher grade heat for raising the temperature of rich solvent before it enters the stripper. Also included is an absorption heat transformer, which is a modified type of heat pump really, on the left of the figure here. The solvent feed to the CO2 absorber provides heat to that. The simulation showed that the extraction steam flow was decreased from 30% of the original specified flow to the LP turbine cylinder to only 18%. Another feature was the utilisation of the CO2 compressor intercooling heat in two ways, on the top right here showing the diagram. Steam ejectors were used as heat pumps in simulations by Reddick and his colleagues in Canada and Zhu and co-workers in China. This slide shows Reddick's work. A flash tank heated with waste heat he used to create the secondary steam to the ejector. Motive steam entering the primary nozzle of the ejector comes from the stripper overhead reflux condensate after evaporation. The energy in the primary steam causes heat from the flash tank to be fed at a high temperature in the steam reaching the stripper. Modelling showed that this system could give 10 to 25% reductions in the amount of steam required from the power plant, with best results when the steam was injected into the bottom of the stripper. In France, Moullec and Kanniche compared various MEA CO2 capture configurations from the literature, modelled as added onto a supercritical plant. Different cases were compared to a reference MEA CO2 scrubbing case representing good performance with about a 12% percentage point efficiency penalty. The study mainly concentrated on modifications to the MEA process itself, and an example is staged feed of the stripper as shown in this slide. The stripper staged feed would be able to take advantage of a closer pinch with indications that there could be a gain of 1.5 percentage points. There's a possibility that better heat exchanger designs could help here, and I'll return to this later. Pfaff and others in Germany examined the effect of using different compression intercooling arrangements, and the results are on this slide. Omitting some intercoolers enabled the temperature level for waste heat recovery to be increased, although at the cost of higher power used by the compressor. Witkowski and Maszkut in Poland looked at other CO2 compression options, including CO2 compression before liquefaction followed by pumping, which allowed compression and pumping energy to be reduced. Although the compression power reduction would certainly be offset by a power decrease in the steam turbine, as steam would be extracted to drive the refrigeration cycle. Other methods of heat optimization have included integration with combined heat and power, as in that small diagram at the bottom there. It shows the system integrated with district heating CHP. Other ones would be addition of low temperature bottoming cycles, for example, using ammonia, and addition of thermoelectrics, which all these could conceivably play a role in the future. The latter two are not currently economically particularly favourable. Obviously, combined heat and power systems are dependent on the location of the plant, making it possible to do this. Harkin and co-workers looked at capture on lignite units in Australia. Using composite curves and linear programming, they showed that CO2 capture retrofits may not incur the large energy penalties previously predicted, and that the penalty could be reduced to 15%. Those are example composite curves that you can see. One oddity was that because the original units were not designed for highest efficiency, it would be possible under certain circumstances to achieve a higher efficiency with capture at certain levels than for non-capture. because of the opportunities for increased heat utilisation, although this wasn't considered to be likely to be applied, as it would need modifications to turbine and generator. Lignite pre-drying is being developed to enable higher efficiencies and so lower specific CO2 emissions in non-capture plants, as latent heat losses can be reduced. Certain types of lignite pre-drying system use very low-grade heat that could make them suited to integration with CO2 capture. In Bulgaria, Pfaff found that all of the heating energy for drying lignite using the dry fining process could be provided by the waste heat in this way. He found that the penalty from adding the CO2 capture at 90% drying of the lignite was only 9.3%, and the efficiency was reduced, as you can see, from 32.9% to 29.8% LHC net. Further measures were predicted to result in the power plant's net efficiency being impacted even less, as you can see there. The originally proposed scope of this study included consideration of new developments in heat exchangers and compressors as possible technologies to use in improving heat integration in CO2 capture systems. On the heat exchangers, an earlier slide showed that these will be using hot streams with low to moderate upper temperatures, so it's only around 80 to 120 degrees Celsius, with heat duties of the order of tens of megawatts to hundreds of megawatts thermal. Moving to very close temperature approaches could increase the heat utilisation and so improve efficiency. Micro-channel heat transfer devices have smaller fluid channels than traditional systems. They may be made of metals, ceramics, such as alumina, or ceramic composite materials, and the channels can be typically 250 to 500 micrometers in size. Attributes of microchannel heat exchangers include volume reduction factors, they're much smaller, by a factor of 5 to 10, weight reduction factors, similarly about 2 to 5, low pressure drops, enabling reduced pumping power, and expanded integration possibilities, actually, from using complex networks in a single device. Most particularly of use here, they can also permit achievement of very small temperature pinches. So they might give a benefit in providing the heat exchange components within CO2 capture plants on the face of it. The overall effect on efficiency of employing such components for closer temperature approaches would depend on the particular design of the system. An example where greater sensitivity has been predicted is for integration options using modifications to the conventional CO2 stripper system. This is the split feed arrangement suggested by the Moullec and Kanniche that I described earlier on today. However, further development in microchannel heat exchangers will be needed to scale up the technology for these sort of applications. The current scale reached in the designs of these heat exchangers is of the order of 5 to 10 kilowatts, for example, in modules that use heat at rather higher temperatures, actually. So despite their offering more compact modules with low pressure drops, their application in this area, which we're concerned with today, is still some way away. For practical reasons, several stages of compression of the CO2 prior to transport are needed to reach the required pressure of 11 megapascals, as usually specified, and cooling is needed after each stage of compression to get to that level. It's typically 6 to 8 stages. The cooling is needed not only to reduce the working temperature of the compressors, but also to reduce the electrical energy required. Utilisation of the heat from the coolers was included in the integration studies I outlined earlier. An alternative type of compressor to the conventional geared types has been designed that reduces the number of stages. This is Ramgen's system shown in the slide. The CO2 flows into a space between a rapidly rotating disc and its casing, where raised sections suddenly constrict the flow, similar to the way air is obstructed as it comes into the chamber of a ramjet. Two stages of compression can be used with pressure ratios of 10 to 1 to get up to the sort of levels needed pressure for CO2 transport. The temperature rises by about 200 Celsius per stage, so higher grade heat can be extracted by the compressor stage coolers. The compressor is also physically smaller and so potentially less expensive than conventional compressors. The IEACCC program looked at these in a study a year or two ago, and they found that electrical power output demand actually would go up a bit, but less steam would need to be taken from the power plant for heating the reboiler because of this heat coming from the compressor. The net effect was an increase in overall net power. Economic gains could make the benefits more significant, but commercialization of this technology will need deployment of CO2 capture on a significant scale. So, summarising the main points from this talk, the output and efficiency of a coal-fired power station unit fitted with CO2 capture equipment will be significantly lower than that of a similar plant without capture because energy will be needed to operate the added systems. Simulations show that the decrease in performance could be reduced by using heat from the capture process. The available heat is low grade, and so there are limitations as to its potential use. The efficiency penalty of adding CO2 capture to a bituminous coal-fired pulverized coal-fired power plant could be brought down from around 12 or 13% to about 8 percentage points, or even lower in some cases. Heat pumps could aid waste heat utilisation, could be integrated in various ways. Lignite-fired plants may offer more options for heat integration, especially if certain types of lignite drying can be applied. Incidentally, local ambient conditions may restrict options or offer greater opportunities for improvements in efficiency with any plant. Have I got that? No, I've still got some more on this slide. New designs of heat exchanger with microchannels could allow closer temperature approaches and potentially increase the heat transferable with some benefit, but not major. These may also enable costs normally associated with achieving close pinches to be moderated. But the catch is that microchannel heat exchangers are currently too small in scale to use. A two-stage CO2 compressor that has been developed offers simplicity and provide higher temperature heat than conventional compressors. It would reduce loss of gross power, and the net effect would probably be a small gain in overall net power with possible cost savings. Well, that's enough from me. Thank you for listening. If you do have any questions, I'll be pleased to attempt to answer them now. So the brief presentation because it's quite summarising, otherwise you get into an enormous amount of detail. So I'll just see if there are any questions. Oh, I see there are two there. Could heat integration be detrimental to flexibility? Well, it could be. It's debatable. I mean, certainly the Edinburgh people, Lucio and Gibbons, reckon that it could actually help. Using those configurations as I showed earlier, they actually reckon that flexibility was going to be possible by using these let-down turbines in different configurations. So it would depend on the system that you have, but I would think it need not be a barrier at all. The other question is, are there any estimates of the effect of these technologies on cost of electricity? That was a question I wondered might come. I haven't found any, but there may well be. Presumably, they should make they will make the cost, the operating cost lower because of reducing the efficiency penalty, and that's one of the biggest contributors to the cost of CO2 capture. So I haven't found any estimates of these, and I was doing really a study that was looking at the means anyway, so it could well be that there have been some studies done. But anyway, I hope that's Okay, I can't see any other questions at the moment. My slides will be available, as I said before, to download as a PDF from the webinar area of our website later on today. And if you missed any, of course, you'll be able to listen to the commentary with them again via Bright Talk. I'll just tell you about the next one, which is, as you saw from the last slide, the next webinar is on the 20th of January, and it will be given by Dr. Stephen Mills. And you can see that he'll be presenting on the prospects for coal and clean coal technologies in Greece. So, as there are no other questions, I'll convey the Centre's good wishes for the holiday season to everyone following our work. Thank you very much, and goodbye. Oh, there's a third question here. I might be able to just... is there any indication of the penalty on the CCGT plant? And there's a fourth one as well. Right, okay. Is there any indication of the CCS penalty on a CCGT plant? Well, it depends which way you integrate CCS on the combined cycle plant. I think you're probably asking about any indication of how heat integration could help with those, could help in, it depends, if you're using MEA scrubbing, you could use similar methods. Of course, there are all sorts of ways of doing CCS on a gas turbine plant, including one method, even using an oxy turbine one of these days. The other question was, thanks for this webinar, I've been looking at heat pump integration to reduce energy losses. It's good to see others have considered this. What are your thoughts? Well, I think heat pumps are a nice idea. I've always liked heat pumps in all sorts of applications, and I think that this question from Thomas Moose, I think, I'll let you. I think that it is an interesting way of doing it, and I've showed a couple of methods there. One, some people have used ejectors, and others have used other sorts of heat pump systems. Certainly, it is of great interest, and I'd be interested in that. Anyway, thank you very much for listening. It looks like that's all, and I'll end the webcast here. Thank you very much.